Welcome back to Statistics. Today I want to introduce you to a second kind of inferential statistics called significance tests. Significance tests are related to confidence intervals, but they're more directly focused on evaluating beliefs about a population parameter, like a population mean, mu. There's a lot of new ideas in significance tests, and so we'll introduce them sort of slowly. In this video, we're going to talk about the ideas that are most closely related to confidence intervals. And then in a subsequent video, we'll introduce some of the more new ideas that are involved with significance testing. So let's see what it's all about. Introducing tests of significance, evaluating beliefs about a mean. As usual, I'm going to start with an example and explain the ideas in terms of that example, and then we'll summarize towards the end of the talk. My example has to do with the law firm of Dewey, Cheatham, and Howe. You can see them pictured there on the right. I think that's Cheatham and Howe we're seeing. I'm not sure what happened to Dewey. But anyway, they're considering a new advertising campaign. A focus group consisting of a random sample of 25 potential clients views a 60-second ad from the campaign, and then they complete a survey that assesses their favorability towards the firm on a scale from 0 to 10. So it turns out that the sample average favorability from these 25 subjects after viewing the ad was 2.5. So that's our X bar value. So not a lot of favorability there, eh? Previous ad campaigns had yielded an average favorability rating of 3.0. So we're going to consider that a population parameter, right? Based on the knowledge they have about their favorability up until this new campaign started. So the question we want to ask is, do the focus group results give us good reason to believe that the new campaign will result in favorability ratings that are on average different from the firm's historical mean of 3.0? So a significance test is going to be the right tool to apply to this question, and in the next few slides we'll just kind of walk through the basic ideas that are involved with significance testing. The very first idea is framing the hypotheses that are in question in a situation like this. In this situation, there's really two competing beliefs that we're evaluating. One is that the new ad campaign won't change favorability at all for the firm. Essentially, that the new campaign won't have any effect. The competing belief, which I'm sure Dewey, Cheatham, and Howe hope is true, is that the new campaign will change average favorability. So you see how I've labeled these with symbols H sub 0 and H sub A. Those are called the null hypothesis, that would be H0, and the alternative hypothesis. Those are going to be the two hypotheses that are in question throughout a significance test. The null hypothesis, denoted by H0, is the hypothesis of no difference or no change. In this case, it would be no difference or no change in that average favorability rating. The ad campaign just didn't have any effect. That's what the null hypothesis is asserting. The alternative hypothesis is the hypothesis of a difference or a change in mu of some kind. And we're denoting that by H sub A. Note that we can frame the hypotheses in terms of the population parameter mu, the true mean favorability rating over the whole population. The null hypothesis is that it doesn't change from its historical value of 3.0. So in terms of our parameters, the null hypothesis would just state that mu equals 3.0. The alternative is that the new campaign will change favorability. So in terms of our parameters, we would simply say that the alternative hypothesis is that the mean mu is not equal to 3.0. And in terms of these population parameters, we can see that the null hypothesis, H0, will always be a hypothesis of equality for the population mean mu, because it didn't change, right? While the alternative hypothesis will be a hypothesis of some kind of inequality for the mean mu. All right, so those are the hypotheses that are under consideration. The basic idea in statistics is to let the data decide, right? We should see which hypothesis is most compatible with the data. The data, or sometimes the evidence we call it, in this case, would be the data that we collected from our sample. It would be the favorability ratings of those 25 individuals. And what's really relevant is the summary provided by the sample mean, the X bar value that we got from our sample data. And you'll recall that that was 2.5. Now, in using the data to evaluate those beliefs, we want to ask a couple of key questions. The first is the evidence or the data consistent with the null hypothesis H0? The idea would be that if the answer is yes, if our data is consistent with the null hypothesis, then essentially we're done. We can go home. There's really no reason to doubt that the null hypothesis is true if the data are consistent with it. What if the data are not consistent with the null hypothesis? Well, then we need to ask a second question. Could the evidence, the data, be consistent with the alternative hypothesis, H sub A? If the answer there is yes, then we should reject the null hypothesis in favor of the alternative. That makes sense, right? Because again, we would be in the situation where the data is not compatible with the null hypothesis, but is compatible with the alternative. And so letting the data speak would mean rejecting the null hypothesis, which is not compatible with the data, in favor of the alternative, which is. So that seems reasonable enough. That, in outline, is the logic of a test of significance. But of course, we have to be a little more careful and specific about what we mean by terms like consistent with the data and so on. So let's take a look at that. We're going to define consistency in a way similar to what we did when we were talking about confidence intervals. That is, a value from the null hypothesis, the null hypothesis being that the mean mu is equal to some value, mu zero. Here, mu zero just means whatever value appears in the null hypothesis. We're going to say the data is consistent with that belief if the sample mean X bar is in the middle C% of the sampling distribution, where C is our confidence level, right? That would just say that the null hypothesis, the belief that mu equals this specific value, whatever it is, just makes X bar a totally typical observation. It means there's nothing unusual or extreme or unlikely about X bar, and so that means that our data, X bar, is consistent with the null hypothesis. We looked at this question when we were studying confidence intervals, and we found that confidence intervals themselves have something very nice to say about this. To ask whether X bar is in the middle C% of a sampling distribution with a given mean, You just have to ask whether that given mean is in the level C confidence interval for mu centered at your x bar value. So those two shaded boxes there are like equivalent ways of deciding whether your sample data is consistent with the null hypothesis. You could either look at the middle C percent of the sampling distribution, or you could look at a confidence interval. What we're going to find, though, is that looking at the confidence interval is a quicker way to make that determination in most cases. In fact, let's look at an example right now. We found that Dewey, Cheatham, and Howe got a favorability rating of 2.5 from their focus group. If we wanted to evaluate the consistency of this data with the null hypothesis that the true mean favorability is 3, we're going to need some information about the standard deviation of our data. And in this case, let's just assume that based on historical data from previous ad campaigns, the firm is willing to assume that favorability varies normally among their potential clients with a standard deviation of sigma equal 1.2. So let's evaluate consistency by looking at the middle C percent of the sampling distribution first, and then we'll look at the confidence interval approach. Thinking about sampling distributions first, if the null hypothesis is true, then the sampling distribution of x bar is normal with a mean of 3.0 that comes from the null hypothesis, right? And a standard deviation of our population standard deviation, which we're assuming is 1.2, divided by the square root of the sample size. That number turns out to be 0.24. So there's a picture of the sampling distribution, and we're highlighting those tails because those kind of represent the extreme observations, the atypical observations, when you're working with a confidence level of 95%. Those tails indicate the observations that are outside the middle 95%. So where does our observed value of x bar fall? Well, our observed value of x bar was the 2.5 average favorability rating from the focus group, and that does fall outside that middle 95% of the sampling distribution, assuming that the true mean is unchanged at 3.0. So therefore, based on the sampling distribution, we would conclude that x bar equal 2.5 is not consistent with the null hypothesis that mu is equal to 3 at the 95% confidence level. But as I mentioned earlier, it's actually a little bit simpler to use confidence intervals directly to assess this idea of whether our data is consistent or not with the null hypothesis. How would that work? Well, what we would do in asking is 2.5 consistent with the null hypothesis at the 95% confidence level is we'd simply form the 95% confidence interval for mu based on our sample mean of 2.5. It turns out that extends from 2.0296 to 2.9704. We interpret those values as the plausible values for mu at 95% confidence given our observed sample data of sample mean of 2.5. So the plausible values of mu given our x bar equal 2.5 extend from 2.0296 to 2.9704, and notice that the value from the null hypothesis, mu equal 3, is not in that confidence interval. So that tells you right there that x bar equal 2.5 is not consistent with the null hypothesis that mu is equal to 3 at the 95% confidence level. And that's again simply because mu equal 3 is not in the 95% confidence interval. And so that's really the most sort of simple and direct way to determine whether your observed data, your x bar value, is consistent with the null hypothesis. compute the confidence interval, see if the null value is in there. If it's not consistent. If it is consistent. So we've determined that our data is not consistent with the null hypothesis. What do we do with that? Well, recall from our previous slide, if our answer to the key question is that the data is not consistent with the null hypothesis, then we should ask a second question. Could the data be consistent with the alternative hypothesis? If the answer is yes, then we're going to reject the null hypothesis in favor of the alternative. So could our data be consistent with the alternative hypothesis that mu is not 3.0? Well, here's the picture from before showing our data, x bar equal 2.5, in relation to the null hypothesis, right? That the mean is 3. But the alternative hypothesis it states that the mean may not be 3, in fact, is not 3. That leaves open the possibility that the mean could be shifted to the left, right? And in that possibility, our data would be totally consistent with the alternative hypothesis, be right in the middle of that shifted sampling distribution. So the answer is yes, our data is consistent with the alternative hypothesis. And therefore, we reject the null hypothesis that mu is equal to 3 in favor of the alternative hypothesis that mu is not 3.0. So that, in essence, is some of the logic of tests of significance. There's some terminology and a couple of other cases we have to consider, so let's move on, then we'll come back to our example. First, there's the idea of a significance level. When the observed data is inconsistent with the null hypothesis at confidence level C, but consistent with the alternative hypothesis, then of course we're going to reject the null hypothesis. But we would also say that the data is statistically significant at the significance level alpha. And alpha is always equal to 1 minus the confidence level. So in our example, we would say that our observed data of x bar equal 2.5 is statistically significant at the alpha equal 5% significance level, because the associated confidence level was 95%. In tests of significance, we usually talk about the significance level, denoted by alpha, rather than the confidence level C. But they're always related. Alpha is 1 minus C, or C is 1 minus alpha, or alpha plus C equals 1, however you want to look at it. They're always related in that way. There's also the idea of a lack of significance, which can happen. What if the observed data is consistent with the null hypothesis, right? That didn't happen in our example, but it could have. Well, recall again from that previous slide, if the answer to the first question, is the data consistent with the null hypothesis H0, if the answer is yes, we're essentially done, right? We don't have any reason to disbelieve the null hypothesis. It's totally consistent with the data. In this case, we would fail to reject the null hypothesis, and we would say that the data is not statistically significant at the significance level alpha. So statistical significance has to do with the idea of, did you have enough evidence to reject the null hypothesis in favor of the alternative at a specific significance level? If you did have enough evidence to reject the null, then you say the data is statistically significant. If you did not have enough evidence to reject the null, then you say the data is not statistically significant or statistically insignificant. Let's take a look at an example. Suppose that in the Dewey, Cheatham, and Howe case, the focus group had returned an average favorability rating of x bar equal 2.7 instead of the 2.5 that we actually observed. To test the null hypothesis that mu equals 3.0 at the 5% significance level, we would again form that 95% confidence interval for mu, this time based on our observed x bar of 2.7. That 95% confidence level turns out to go from 2.2296 up to 3.1704. So notice now that the null value, the value from the null hypothesis of mu equal 3, is in the 95% confidence interval. Therefore, it is totally consistent with the belief that mu is 3.0 with the null hypothesis. Thus, we would fail to reject the null hypothesis at the 5% significance level. And we would say that the data are statistically insignificant at the 5% significance level. A little bit more terminology. A significance test that has the same basic form as the one we've been considering, that is, the null hypothesis is that mu is equal to some certain value, which I'm calling mu sub 0 here, versus the alternative that mu is not equal to that value, is called a two-tailed test. And that's because when we're trying to determine whether the data is consistent or not, we're looking at that, those both tails. We look at the middle 95% or the middle C%, and whatever falls outside of that in either tail, left or right, turns out to be, statistically significant. The value mu0 from the null hypothesis also has a special terminology associated with it. It's called the null value for the test. So we can summarize. For two-tailed tests, that is, tests of the form H0 mu equal mu0 versus HA mu not equal to mu0, at a significance level alpha, we carry out the following steps. First, we obtain an SRS from the population and compute the sample statistics. Then we form a level C confidence interval where C is equal to 1 minus alpha, 1 minus the significance level. We form that confidence interval for mu using our sample average x bar. Then we look at and see whether the null value is in the confidence interval or not. If that null value is not in the confidence interval, we reject the null hypothesis H0 in favor of the alternative at significance level alpha. And we say the sample data is statistically significant at the significance level alpha. On the other hand, if the null value mu0 is in the confidence interval, then we fail to reject the null hypothesis at significance level alpha, and we say that the sample data is not statistically significant at significance level alpha. So there you have it, our first introduction to the important idea of a significance test. As I said, we've been mostly relating this to what we already know about confidence intervals, and that is a very important thing to do. But there's more to be said here, and we'll begin talking about that in a subsequent video. In the meantime, take care, and I will see you next time.